Hello. So we thank you all so much for joining our session here today. This is one of our monthly information sessions, and this is actually the first one back after summer, which is very exciting. We're getting back into the fall months, so it's being really, really nice. And yeah, feel free to turn off your video, and there's also Zoom settings where you can turn off incoming video in case you have weaker strength. I'll be sure to turn mine off when I'm not speaking, and I think I would encourage our other speakers to do the same in case you have a little bit of a laggy internet. So again, if you're calling in, be sure to mute your phone, and if you're using computer audio, we try to keep all participants muted. During the Q&A session, after all of our speakers have presented, we'll have about 15 minutes or so for everyone to ask questions, and you can ask questions in the chat, and I'll be sure to read those out loud as well. And all of our information sessions are recorded and posted on our Learning Network website, which I point out as especially important for this information session because this is actually a part 2. We did a bit of a deep dive into topobathymetric data and how it's collected and used with all of our same speakers before. And today we're going to be focusing a little bit more on the storms aspect. So just a reminder that if you like what you hear today, there's also a part 1 that you can listen to and garner a bit more information. I also want to invite everybody who has access to the chat to go ahead and introduce yourself, say where you're from, and maybe one of your favorite things about fall. So my name is Megan Pitas. I am Program Coordinator for the Alaska Climate Adaptation Science Center. I also help facilitate some of these sessions with our Alaska Tribal Resilience Learning Network. Our offices are located across a number of regions, all on Indigenous land. Everywhere we work and play is Indigenous land. So our UAF campus is on Trothiada. The name was actually gifted by Chief Peter John of Minto to the university in 1990. And I am based on Daniina Islena or Dagaikak, also known as Anchorage. And we also have a number of team kind of based all over the state to be responsive to different regions and to help support a different manner of things. So we also have another one of our team members, our tribal liaison, Geraldine Kelly, who's based in Quinnahock. So as we go ahead and get started today, again, this is part of our normal Tribal Resilience Learning Network sessions. And we have a number of different supports available to folks, one of which is the e-bulletin, which I think is probably how a number of you have heard about it, either our e-bulletin or our listserv. And we also have regular trainings. We offer one-on-one technical assistance. If you're interested in climate adaptation aspects, just go ahead and shoot us an email and let us know. And with that, I would like to welcome our speakers for today. And this is also kind of the broader order of those that will be speaking. We have Kelsey Ivanoff, Erin Trosham, Maya Hayden, and Lee Erickson. And I actually just saw Erin pop in. Hi, Erin. And so this is kind of the flow of things that we'll be talking about today. And I will also let them introduce themselves because they will do it better than I ever could. So with that, I think I'm actually going to hand it off to Kelsey. And Kelsey, let me pull up your slides really quick. And take it away.
All right. Hi, everyone. My name is Kelsey Ivanoff. My Inupiaq name is Kasungnalak. My Yupik name is Abazanak, and I am from Unalakleet. I was raised here, kind of lived everywhere, and I ended up coming back after my daughter was born. I moved back about 6 years ago. I am currently the city administrator, and not for much longer. I'm moving on from this position, but it's been really good, really. I've been in this position for about 1.5 years, and I was the mayor before. When we couldn't find a city administrator, I kind of just stepped into the role since I was already doing the work. I yeah, we have over at the city, we have a lot going on. We participated in these workshops with USGS and UAF, and that's kind of how we got involved with all of this. And then the tribe applied for a grant through the Learning Network, and yeah, so it's been really good to connect with everyone. And what I will do is kind of explain Unalakleet a little bit. This is Unalakleet if you've never been or never seen it. It's about 140 miles southeast of Nome. And we are very lucky to have on the lower left side of the picture, we have a seawall, which we're very lucky to have. You can barely see the dark part that kind of starts towards that road, turns into lighter rock that came, and then it turns into a steel piling where the dock is. We got that was used to be a gabion wall, and that didn't last very long. That was too straight up and down and just washed all of it. All the force of the ocean kind of created it to lag a lot, and it just didn't last very long being as beat up as it was. So we have this now. It has done its job very, very well. We have yet to flood since we've had this. And I remember waking up when I was younger when we didn't have this to waves. I live like right at that bend of the road by the darker part of the seawall on the ocean side. I remember waking up to waves crashing against our house. So none of that has happened since we got our seawall. And you can see it's all happening right at the mouth of the river where the river meets the ocean. And then we have the slough. In recent years, our fall storms are creating bigger water surges. Actually, not even fall. I'll go into that. But in that slough side is where we're getting a lot. That's where we worry now. Now that we have the ocean side taken care of, the slough side is where everything starts to come up, and we have a bridge that I've pointed out, and that is our evacuation route, which we're also very lucky to have. And we have 3 hillside subdivisions, and our landfill is also located out from that bridge. And you can go to the next slide. So I was talking about the storms, how they used to be called fall storms, and we still get them, every fall, but it's becoming a trend where we're seeing them early in the year, and we're starting to flood into winter even, where it's coming over the ice. And so we used to have these winter storms where it would happen when we had ice to protect us. And that is the seasons are kind of merging, and it's creating, because we don't have the ice to protect us, we have these issues of the water rising higher than it used to. And these pictures were from Merbach, kind of before and after. It's hard to gauge when you see pictures of high water if you don't know what it looks like before. So I tried to get some pictures of when we were at high tide, and then pictures of during the storm. And so yeah, all of this is on the slough side, on the left side. That's what I was talking about. That's where we have to worry about now. And we see these big water surges on the inside now. Whereas in the past, we used to just have to worry about water intrusion on the ocean side. And you can move to the next one. And then this is in the February after Merbach. So our storms are, because we don't have that stable ocean ice anymore, you could see in the left picture there, thankfully we had that little bit of barrier, but so it didn't push any debris or anything up, but we had a huge water surge. And this was, I think, like a day or two after Iron Dog came through. And this is in the middle is where their trail is. So So we're seeing a lot of this in the winter as well, and that affects our river ice and just kind of creating conditions that aren't ideal for everyone going ice fishing, and it's a pretty well traveled. And then we have the Iditarod coming through the next month after this, and so that was a big worry. And thankfully, it ended up coming down, but uh, we see how often we see these storms. Last year, we got an insane amount of snow. Like I hadn't seen it like that since the 90s. So the pattern of what we're seeing with these storms um is changing, and that's what's and then our evacuation route, that's because it's flooding on this side, our evacuation route gets close to flooding. So we would have nothing after that. um and I don't remember if I had another. I think I have one more. Oh, a couple more. So Unalakleet, we opted to not do a relocation when back in maybe like 20-ish years ago when we first started having these big fall floods. They opted to kind of do a slow relocation. So the idea of this rock wall that we have kind of buys us time in our current location to do a slow migration to the hillside. So we have three hillside subdivisions. One is owned by the city, one is owned by the Native Corporation, and the third is a Native allotment hillside. And the city, was gifted the first hillside subdivision so that um, because the corporation believed that we could develop it quicker than they could with their own, because they're limited um to shareholders being able to build on their land. So that the top right picture is the Elder facility, and that's also where the Second Hill subdivision, and the bottom picture is the First Hill subdivision. And super exciting on that First Hill subdivision is where our new pool is being built. So any new infrastructure, we really try to encourage, especially something that long-term like the elders facility and the pool, we really try to encourage everything to be built on the hillside. That's going to be a long-term, because our belief is eventually all of this is going to be where we're at right now, is going to be underwater. You can go ahead and go to the next one. So when we started working with the learning network, uh we went to these trainings, which were really great. And we hired somebody to look at all of these plans to create an outline for a climate adaptation plan. But these are our three main plans that we have: our local economic development plan, our hazard mitigation plan, and our long-term transportation plan. I know the long-term transportation plan they've really adhered to that. That's with COERIC. And that dealt with in that plan had included paving of our roads, paving of our runway, the road leading out of town, the bridge, the seawall. A lot of those projects we did end up getting. And then our hazard mitigation plan, we thought that was super important to get, because that does help you get funding to help you get this infrastructure to help you protect your communities against these storms that are becoming, through the entire year. They're not fall storms anymore. They're through the entire year. And yeah, so we have an outline now. That project was ended, and they've continued to work with that, and they're working on expanding it and have hired another person to work on that after we had our last person doing the initial outline. And yeah, it's been an ongoing project, and we're super excited to see where it goes and keep working with USGS and UAF on this coastal mapping. And I think that's all I have.
Great. Thank you so much, Kelsey. Yeah, I think that this very much in line with what we've been hearing about the fall storms not just becoming fall storms. They're storms year round. They can happen at any time. And with that, I think Erin, you are up next.
Thanks. So I thought I would just give a quick talk update rather than slides this time. So I'm Erin Trosham. I'm a research assistant professor at the Institute of Northern Engineering at the University of Alaska Fairbanks. And I'm located on the Trothieta campus on the ancestral lands of the Dene people of the Lower Tanana River. So I lead the UAF coastal mapping program. And so we work with the Army Corps and one of their programs called JABLTech, the Joint Airborne LiDAR Bathymetry Technical Center of Excellence, who also is part of the National Coastal Mapping Program. And what we do is help support flying of, it's called topobathy LiDAR. So it's a special instrument that is on a plane, and when it flies around, it shoots out laser beams with green light, and when it returns a signal, we can see the depths of not only the land but also the water. And so if you saw any planes around this summer, those were not our planes. We unfortunately did not fly in Alaska this summer, but we've been doing data collection in 2018, 19, 21, and 22, and 23 as well. So we're getting out the 2018 and 19 data is available publicly. The 2021 and 2022 data is coming out right now. And we still have to process the 2023 data. We were able to hold a workshop in Unalakleet. And so in February, and it's great to see some of the participants from the workshop on the phone with partnership from QUERIC and the USGS and the Climate Adaptation Science Group, which is hosting this workshop. Yes, we've been hearing about a lot of flights. And so we're happy to talk more about that actually, because I think this is a really key point of conversation actually. So a couple updates from our side of the project. Some of the things that we've been hearing is that there's a need to talk about data, but as Melinda has reminded me, not necessarily starting with the data itself. So even though that's a lot of what we do. So we've been really rethinking about how to provide more space to have these conversations and to have engagement. So some of the things that we've been doing around that is we've been printing 3D models of data. So we brought some models of Unalakleet and Golovin and Elim with us to our workshop. We're going to be printing off some more models of Nome and Shaktoolik and Shishmaref this fall. So we're really interested in how else can we be able to facilitate information and sharing about where to collect new data, but more importantly, what we need in order to be able to do things with it. And so some of the things that we're interested in is where do we need repeat data? And so we had a chance to just start to take a look at some of the time series analysis from Unalakleet this summer. So where we've flown over Unalakleet several times, we can look at changes between 2019 and 2021, both below and above the water. One of the other things that we're up to, and I would love to hear more feedback from this group, is that when we held the workshop, there's just a lot of things to catch up on. Whether you're coming at it from the community planning side, whether you're coming at it from the flooding side, as Maya and Lee are going to be talking about, or you're coming at it from the data side, and understanding some of the coastal processes and how we quantify and capture them. So we are working on an EDX class about topobathy data and its applications. And so that'll be a free online class available from UAF. And we're just starting to develop the course content and outline right now. So if you have ideas about what you would like to see in that class, if you have questions, please contact me. It would be great to get feedback and understand what you want to know and what we could cover in a format like this. The other thing to know is that we're having a big meeting in Anchorage in October 22nd to 24th. The annual Jabal Tech meeting is coming to Anchorage. And so yeah, we'll be participating in that. And so if you have any concerns or you happen to be in Anchorage and you'd like to know more about coastal mapping, definitely contact me. I'm happy to share the registration with you and to talk more. So with that, I'll hand it over to Maya and Lee.
Thanks, Erin. I think Lee is going to be presenting some information today, so hopefully she's on and able to share her screen.
Okay. Thanks, Maya.
Yeah. I can see you.
Okay.
So I'll just quickly introduce myself. I'm Maya Hayden. I am with the U.S. Geological Survey. I lead our outreach and engagement efforts, particularly around these future flood products, and really serve as kind of a bridge between our science teams and folks that are using the information for decision making, such as yourselves. So I will pass this over to Lee, and just so you know, Lee, yeah, we can see that document. There you go.
Okay, I'm sharing my whole screen there, yes. Okay. Hi, so yes, my name is Lee Erickson, for those of you who don't know me yet. I live down in California on the Ohlone tribe area. My original ancestral lands are actually in Sweden. That's where I come from. So also from the very northern reaches of the globe on the other side of the Arctic Ocean. I've been here at USGS for about 20 years working as a research oceanographer. And I've been studying the Alaska coastline for more than a decade, looking at climate change impacts and such. And so I'm going to be talking about some of the work that we've been doing. So this is a presentation that Maya and I put together, but we're doing, go through here with the slides. Can everybody see the slides okay?
Yeah, they look great.
Okay. So the slides here are the work that I'm going to talk about a little bit today is presenting on behalf of our core USGS modeling team, Nita Engelstad, Case Naderhof, who's actually with Del Taurus, Alex Narrison, Ann Gibbs, and Rich Boussard. And this work is partly funded by the FY23 Disaster Relief Supplemental from the MERBOC, and also from CASC, and also from our internal program, CMHRP. So what we were thinking today, this being the learning network, we thought we'd like to approach these 4 topics to have hopefully people who are listening in here to be able to explain with an example to a colleague of what are the components that add up to a total water level and why are we using those in this work. What is meant by a 100-year storm or a 1% annual exceedance probability. Also, we'd like to give you a little preview of how storms are likely to change due to climate change along the coast, and how it's envisioned using the USGS Coastal Storm Modeling System, COSMOS, how we are using the storm scenarios for both long-range planning and emergency response. So I'm going to start here with a pretty picture, but there's a lot of information on here. But the point of this, what we're trying to show here, is to talk about the concept of total water levels at fronting beaches and open coast areas primarily. So if there's an equation at the very top, total water level equals 1 relative sea level rise, 2 tides. Those are the astronomic tides that come with the revolution of the moon and the sun. We're going around the sun and the other planets as well. And the third component is storm surge and seasonal effects. Those occur during when the storms are happening. The seasonal effects occur throughout the year, but they are also affected by the storms. River discharge in times of high river flows and high rain, then there's a plume that comes down and often meets with the storm surges, and that causes an extra rise in the sea level. And then the last one is wave run-up. So wave run-up being the waves when they approach the shore from offshore and make it to the beach, we get a sustained long-term wave we call wave setup, and then we get intermittent uprush of the waves. And together we call that wave run-up. The text that's in the rest of the figure is a little more on the details that I just kind of summarized. If we take a slice through a cross-section, if we look at it this way now, and look at all of these components, this figure here is meant to summarize about the ranges that we see along the western and north coasts of Alaska. And what you're seeing here at the bottom is the datum of mean sea level. And if you work your way up, you can see the next one is the mean high or high water, and that is in the areas particularly where we have a big tide difference. Then we like to look at elevations, any flood elevations that might occur above that mean high water, because the mean high water is something you see frequently on a regular basis. So it's anything above that that's really of concern. So compared to today, we have a mean high water today, and then we have anticipated sea level rise on top of that. It can be anywhere up to 10 feet, depends on location and sources, what the current prognosis is. On top of that, we also have the sea level anomalies. So these are caused, as I sort of mentioned in the previous slide, they're caused by thermal expansion and also by flows with salinity stratification, and also bathymetry and the currents that are going along the coast. All those things add up to annual and seasonal and storm-driven sea level anomalies. Then on top of that, we have storm surges, which occur during big events of passing storms. That's an elevation of the sea level due to the wind that's blowing over the water, and it can also be because there's a low pressure system. And if you have low pressure, then the water will just rise by itself. On top of that, we have a river discharge, which, as I mentioned, can cause a bulge if it meets up with the storm surge or the tide. And then lastly, the wave setup and run up, which can also reach up to another 30 feet. So all together, these are the factors that we're trying to include in our forecasts and projections and in looking back to figure out what the flooding has been and what the flooding might be due to all these factors. And important, so how much flooding occurs from a particular total water level, all those components adding up to be a total water level, depends on the nearshore bathymetry, topography, soil type, and other factors. And other factors include soil infiltration and what construction is there, etc. So I wanted to just point out here, if you have a particular total water level, it may mean something different depending on where you are. So if you have a milder beach slope and if you have a different topo elevation, you get different flooding, obviously, from the same total water level. What we're talking about here today that I'm going to focus on is the estimated total water levels based on data that is at a point nearby the shore. So the arrow that you see here, this is the location that I'm going to be looking at the data for the water levels and the waves that eventually cause the run-up and the sea level anomalies and the tides and all of that. And I just wanted to point out that once we get on land, it can be a little different than what the offshore or near shore data tells us. So the storm component of this total water level, and to some extent the sea level anomalies, depend on particular storm systems, the storm system's trajectory, speed, size, and magnitude. So I thought I'd just summarize a little bit on some background that I think most people are aware of, because especially the people who are folks on this call who are living it on a daily basis. Storms that impact Alaska's west coast typically follow either come from the north through Siberia or the Aleutian tract across the Bering Sea. And the frequency of those tracks changes based on the Pacific climate regime. So some years we have a PDO, some years we have El Niños, all those cycles, not annual, but they go on decadal cycles and multi-decadal cycles. But they're also changing because of climate warming, global warming in general, and climate change. The wind direction, storms over the Bering Sea and Bering Strait typically produce westerly or southwesterly winds over the Bering Sea and easterly winds over the Chukchi Sea. And the wind strength is associated with storms can be persistent, and oftentimes because these storms stall and remain in place. But the trajectory of the storms and where they go has a key result on what's experienced at each community, what waves result and what storm surges come to each community. For example, here, this is a little short brief of Merbok event, which was we're at the 2-year anniversary, almost to the day, was happening 2 years ago today. So if you can look at this animation here, you can see, imagine yourself standing in Hooper Bay versus Nome, right? The direction that you see from that storm is very different. And that results in, for example, here, this is for Merbok. These are actually sea level anomalies that were driven by the storm system. And you can see through time how it changes through time and geographically. And I think, yes, there you can see at the end there, it accentuates in Norton Sound because of the geography and the track of that particular storm system. Another thing to consider when these storm tracks go across the region is the timing of events, and particularly the timing of the tides. In this case here, I'm showing on the left-hand side is the big blue circles summarize the tide range at several of the communities, many of the coastal communities along the north and west coasts, and they're scaled accordingly. So you can see on the north slope, the tide range is very small, and it increases generally as we go south and is higher in Norton Sound, again, because of the geography of the sound there. It focuses the water, you can say. On the right-hand side, I have an example of a time series. So on the top figure, the top plot, the x-axis is the Merbok dates, September 17th to the 20th in 2022, and water elevation on the y-axis, feet above mean sea level. I plotted it here against mean sea level just because it's easier to look at this way. So what I wanted to show here is that let's look at the blue line for storm surge, and the sea level anomaly had this peak here. And the tide, it luckily coincided with a tide that was almost at zero mean sea level. So if you combine those two, we end up with the yellow line. So we ended up here at 12 feet or so. Had Merbach instead occurred during a higher tide, then we would have had even worse consequences, as you can see on the graph below. And the scale is the same, so you can compare one to the next. So timing is really important, and often, and when you come down to areas with the higher tide range, it can be affected more. So how many times per year might we get a storm that results in a certain total water level when we're looking at that? So I was going to talk a little bit about return periods here. This figure here is a time series that's generated now through modeling. And it goes from 1979 to 2022 through 2022. And this is Unalakleet in this case. And we plotted the total water level estimates. And that's from all those components that I talked about previously. And what we can do is then look at all the peaks over time and count up those peaks and try to figure out, okay, how many times do these occur? And what are those? We want to describe them in extremes. So for example, here, if we look at maybe the 15-foot above mean sea level occurred about 10 times over the course of this record here, which is 44 years. So one might expect such a total water level height to occur about 25 times over a course of 100 years. And we can convert that into probability space. So this is the same data, but now we plotted it against what we're calling return periods. And the return periods are equivalent for an annual exceedance. That's another way to say it. It kind of has become a standard to be used in both engineering, planning, and also FEMA. Back in the 1960s, it was decided that the annual exceedance probability, or 100-year flood, is the basis for the National Flood Insurance Program. And it's meant to be an estimate of the long-term average recurrence interval. So it doesn't mean that it's certain that we're going to have a 100-year event in 100 years, or that we have a 1% chance of it happening. There is a 1% chance of a 100-year event happening any one year, but it doesn't necessarily mean that it will happen. It is an indication of a long-term average. So when we're and trying to get at the 100-year event, oftentimes we don't have records that are long enough, and so in this case here, plotted up the records that we have been able to hindcast with high quality data back to 1979, and that leaves us with 44-year long record. But we want to know what the 100-year is. So we have to do this fit through the data. And we can now say that the 100-year return period for the total water levels are estimated to be here. So that's 16, almost 17 feet. That's, oh yes, I wanted to say, so this is a typical way of doing it, one that it's a very standard practice to convert it like this to return periods and fit this line is a fitted GPD or GEV or log linear fit, and the blue is the uncertainty range that's going through there. What we've been doing here is, as part of this work, is we've come up with a new hybrid numerical statistical multivariate joint probability method for finding covariate extremes. There's a lot of words there, but what it is, the intent of it is that we need to know what the extreme events are, but we need to know the joint probability of events because storm systems are synoptic. So we want to make sure that we're capturing wave heights and storm surges that could potentially occur together, not the ones that are from different storms and assume that they are occurring together. We don't want to go there. We want to make sure that it's that there's a high likelihood that they would occur together. So in order to account for those dependencies, we developed this new method using a Monte Carlo approach where we do a lot of sampling. So what happens here is it's the same idea in that we plotting up here the return periods versus the mean water level proxy or total water level proxy. That's the blue dots, that's from the data. And then we generate 200,000 plausible combinations of wave, storm surge, sea level anomalies, and tides for each location, and find the most probable combination of the total water level components for each of the return periods that we're interested in. And that's what those red boxes are here. Those are the most probable. And I'd like there's a lot of information and we could go into that a lot deeper, but I think we save that for another time. If people are interested, we could do a deeper dive into that. I wanted to go back maybe a little bit just again to the 100-year storm, which is the most talked about event and used often, like I said, for FEMA and for design purposes. Often design purposes are also used in the 50 and 30-year return probability. So let's look at the 100-year storm. What does that mean? Re-emphasizing here on the left-hand side, it's so not just the 100-year, I'm sorry, also the annual storm. The left-hand side jar has the annual storm. When we're talking about the annual storm, that's a storm that's very likely to occur in any one given year. A 10-year storm, then you have one blue ball and 10% probability of it happening in any year. If we are talking about the 100-year storm, then for any 1 year, we can flip that around and say we have a 1% chance of it happening in every year, in any year. But again, I wanted to point out that these probabilities represent an average over time. So it's not necessarily it's going to happen that way. So doing the extreme value probability analysis of the total water levels and looking at the 100-year and the annual, 10-year, 20-year, and 50-year, we've now been able to summarize all these total water level estimates for each of these return periods for all of these communities going from Kaktovik all the way down to Togiak. You can see the bar plot here on the left-hand side. So the green bar plot is the 100-year return period levels, and then it goes down into the annual return period levels. Because we've come up with this multivariate joint probability analysis of doing it, we can go back to the data and also look at what are the relative contributions of each of the total water level extremes. So here on the left-hand plot is showing the 100-year return period total water level components and the relative contributions of each. So for Kaktovik, for example, you can see that about half of it is due to non-tidal residuals and half of it is due to wave run-up. And if we work our way down the coast, we get more and more of a prevalence of the tide, which makes sense in that the tide range is higher the further south we go, so that chances are that we are going to be hitting a storm when we have a tide that's over the mean high water line. We've also been working on doing these types of computations for the future time period. And for the future time period, we used storm patterns, like I was showing you for the Merbach, so simulating those, but at the future storms, and sea ice as well, from 4 different CMIP6 climate models. And summarizing those is on this plot on the right-hand side for the 100-year total water level. And it shows the projected percent change of the 100-year total water level by the size of the bubbles. And then the colors refer to which component is the largest contributor to each of those changes. And as you can see, the wave run-up are often the largest contributor on the north slope. And then we get down to it becomes more water level dominant in the bay on the west, on the north in the sounds on the west coast, and then the remainder is about equal. Both water levels and waves contribute to the increase. Going back to suss out, okay, why is it the waves? On the North Slope, for example, we can make clear linkages with some previous work that's been done, that the increasing wave contributions are related to the increasing duration of the open water season. This plot that you see now on the left-hand side, the top one here shows the wave heights. I believe this is in Prudhoe Bay, from 1979 through 2050, basically, 2049. And you can see the solid lines are the average for moving mean or over the year for decades. And you can see that the wave heights, for example, for 1980 to 2009, they peak in October, they creep up and peak in magnitude in October, and then they die off in mid-November. And then if we keep going through the years, so the red thick line, you can see that the width of this red thick line becomes wider. So we have more and more storms that are able to hit the coast, because if you compare it to the plot below, you'll see that the open water season, when the sea ice comes back in for landfast ice, is also extending. And so it's the extension of that open water season that gives us more opportunity for increasing waves over the whole duration of the year. And you also might note that the maximum height that it reaches is not that different from the previous decade, 2030 to 2040. So we've reached the amount of open water matters less in the future, because we're going to reach a tipping point where that fetch is not so important anymore, but the duration of that open water season is what's important. I'm almost done. So the critical inputs, what I've been talking about here is the total water levels at some offshore point near a grid, overland flow model grid. So in the middle here is an example of a little section of the Unalakleet overland flood model. So the total water level components that we've been talking about here for the 100-year event, 1-year event, and so forth are the ones that we feed to this model at the left-hand open boundary, as we call it. And we do put that in with a variety of different sea level rise scenarios, and then can assess what the hazards are, the flood hazards are. What's also, as I mentioned before, extremely important for both the nearshore bathymetry and what happens over land is the accurate topography and bathymetry that Aaron was talking about, and that we're working with Aaron and others on getting into our models for high accuracy. We are also exploring, rather than, we're exploring, rather than putting in the future changes of the forcing data in the offshore region, we're exploring replacing that with forecasts from NOAA and using that for National Weather Service's forecasts. We're also working with the National Weather Service in employing the database that we're generating with these model simulations of future scenarios and the flood maps that will come out of it. From that work, we will be producing this kind of database of community scale overland flood maps and erosion for individual storm events. And so what we're building with that is a query system where in the forecast mode, when there's a storm happening, we can look at the forecasted waves, wind, surge, and precipitation, and then go back into our database that we're developing here at USGS and find the corresponding map. And that map then can be used by the National Weather Service to make an assessment of what risk might be coming for the impending storm. And they will amend that obviously with other tools that are available to them. for all of this work, we need to verify our models and we need to calibrate them to make sure that they're doing a good job. And that information that's collected on the ground is so critical. And we just so much look forward. We so much appreciate working with community members and community leaders, and really appreciate and hope that we can continue to get input um, from residents and observations. And what I've shown here are some flood staffs that have been put in this last year and the previous year as well. This is an effort that's led by Rich Bouzzard, and along with DGGS and others, they've put together pages. You can see the QR codes here on the right-hand side, and these pages list all the flood staffs that are currently available. And there's also a new Facebook group where you can post flooding photos. Those are really helpful for viewing where and how high flooding is. So just as a summary here, here's another QR code for more information on this particular work and project. And as the work that I talked about today with these total water levels in the nearshore region, we're applying those both for the long-range planning and for emergency response, with end users in mind that are both at the local levels, state and federal levels, and as well as the National Weather Service and emergency responders. So and that's all. Thank you.
Great. Thank you so much, Lee. I really appreciate all of the time you took into putting those models and projections, and to all of our presenters for the time you took to come and speak to us today. We do have time for some questions, and I don't know if any of our presenters can stay late to maybe answer some questions. And I know last time they were really forthcoming with their contact information. So if you have questions about anything specifically, you can direct it to them and I can send that to all of you. But yeah, for those of you that are able to stay for the last couple of minutes, here's also our contact information and an announcement before people if you need to hop off. Yeah, what questions do people have specifically about for our speakers and presenters today? Yeah, Nick, go ahead.
Hi, everybody. Thank you very much for all the presentations. That was super informative, and I appreciate the range of efforts and perspectives that were being presented. I wanted to ask, I'm curious, kind of like, as these models improve and the projections of, what is, inevitably going to be, pretty challenging circumstances with sea level rise and storm surge as we move deeper into the 21st century. What's the relationship between this information, the creation of local kind of hazard mitigation and emergency preparedness plans, and the insurance? Because insurance companies, the more information they have about risk, my understanding is that they will alter their practices and insure things differently, as is already happening in Louisiana and parts of the Gulf Coast. So I'm wondering kind of like what the relationship is between between what Kelsey was talking about in terms of city management and kind of building these plans and being able to prepare yourselves for these circumstances, and then the kind of ways that risk is managed at the level of insurance companies, the National Flood Insurance Program. Just if anybody has insight into that, I'd be curious.
Great question. And I
Yeah,
think
my only experience so far has been with our tank farm. I'm not sure with like homeowners or anything at this point. But I know with our tank farm insurance, they are a lot more receptive to insuring giving us flooding before. I know it was difficult in the past, but now that we do have these plans and we do have models to look at, they are a lot more receptive to insuring our property. And our tank farm is like on the slough side, right outside of the bridge, right up there, about a quarter mile from the bridge.
And that's been contingent on your ability to demonstrate that you all have taken every precaution necessary to like cite and protect those assets. Yeah.
Yeah.
Thank you.
Yeah, thank you, Nicholas. And I did get a question in the chat. I know, Aaron, you were talking about a few of the different communities that this data is collecting on and some of the pilot communities and pilot projects. And I got a question about Shaktoolik specifically, if you could just reiterate what you were saying about Shaktoolik and their involvement.
So Shaktoolik participated in our 4-community Unalakleet meeting, and so we printed off a small 3D model for them. Our plan is to go actually out to Shishmaref this fall and do some additional community engagement work out there. And so yeah, but if you've seen the Shishmaref model and the Shaktoolik model, and you have any feedback from us, we'd be happy to hear it actually, because we've been, like I said, looking at our 3D models, and we're doing a bunch of work to figure out how to print them more effectively. Like I said, how to do some more engagement work around those models. And by models, I mean they're like actually like 3D printed, like plastic printed models, essentially. Yeah, I should have brought a picture of them. So yeah.
I know in Unalakleet, people love them. We just have them, I put them, ours, just right on our conference table in our council chambers. And anyone who comes in for city business, it like catches their eye right away. And they're like, oh, this is really cool to see. And so yeah, people really like it here.
Good deal. And yeah, I also just wanted to reiterate that we'll have the recording and the slides posted on our website. So especially all of those amazing graphics, Lee, that you put together, if you want to look at the specific community and what they look like for that. You absolutely can. And again, I think all of the presenters seem to be open to, if you want to contact them directly. They're very busy people, but I can attest that they're very responsive. So if you have any further questions, yeah, I can stay on for a few more minutes, and whoever presenters can stay on too. But nothing else. Thank you so much for your time and for listening and for presenting. We really, really appreciate it. I think these sessions tend to be so helpful. And one last plug, that if you want to hear more about how the data is collected and how these models are produced, we do have that part 1 that you can watch on our website. So just a quick reminder. With that, I'll stop the recording and stay on for a few more minutes.